For this problem statement, we have determined the horizontal and vertical components of reaction at pin C. So we have pin C, we have pin A here, we have a member AB connecting to member BC over here. We have a external moment being applied as well as a external force, which is 400 newtons. So in this case, find the reaction components of C. Now, one thing you could do, of course, like we've always done, is do the sum of forces and moments for the whole structure. But in this case, we see we have two hinges, so we're going to have four unknowns and we only have three equilibrium equations to apply. So we're going to have four unknowns, and with only three equations, we won't be able to fully solve the problem. So in this specific case, it's best to split up the components and first analyze one and then go ahead and analyze the other. So let's go ahead and do this let's go ahead and do member AB. So for member AB, we have a reactionary force at A. So we have AX here, and so we have a reactionary force at A. We have AY as well as AX. Now, of course, this whole structure is in static equilibrium. That means this member is also in static equilibrium. So this member at pin B has to have equal and opposite forces of AY and AX. So we have BY equal and opposite to AY, and we have BX equal and opposite to BX. So now to make it a little bit easier to explain this, I'm gonna go ahead and draw the magnitudes of these components. So here's gonna be the magnitude A, right? And the magnitude B, equal and opposite. So let's go ahead and do member BC. So now looking at it from the perspective of member BC here at pin B, we're not going to have this magnitude B going down. We're going to have it equal and opposite, right? There you go. This is going to be the force. So now we could actually analyze only member BC just by drawing the magnitude of the force that's basically being caused by member AB. And a rule of thumb is when you have these weird geometric members, you could just draw a straight line of action through both of them, and that will be the position of the force of that member here. And luckily we have the rise and the run, right? We have that it's 1 meter going up, and this one is actually also 1 meter as well. So we have the rise and the run. Essentially, we have the angle of that magnitude of the force. And now we are able to do the equilibrium equations here for Cx and Cy and solve accordingly. So I'm going to go ahead and call this F A B, and let's go ahead and apply the static equilibrium equations only to member BC here. So first I'll do the sum of moments with respect to point C. Of course, counterclockwise is the positive sign convention. So doing the sum of moments, we have a 800 newton meters moment, external moment being applied to this member. We have the force 400 newtons times 2 meters, which plus the force AB. We do the x component part, so it's adjacent over hypotenuse, and the perpendicular length is 1 meter. Take away FAB is opposite over hypotenuse times the perpendicular distance, in this case is 3 meters, is equal to 0. So we see we only have one unknown here, and so we go ahead and solve for that one unknown, which gives us FAB is equal to 1131 newtons. Now having this, we're able to solve for the x and y component of the reaction C. So let's go ahead and do that. So sum of forces along the x direction, we have negative Cx plus 1131. We're taking the x component of FAB, so it's adjacent over hypotenuse, and this is equal to 0. So Cx gives us 800 newtons is the x component. Now let's go ahead and do the summation forces along the y direction. And from here, we solve for Cy, and we get negative 400 newtons, which basically means it's 400 newtons in the downward direction because of that negative that we got. Our assumption was incorrect. So now you could go ahead and double check when it comes to the slope, the angle of this force. You could go ahead and do the sum of moments with respect to point 8 for this specific member, and you'll see that Bx is equal to By, so there's a 1-to-1 ratio and basically gives you the same angle here. And so this is a problem. This is how you solve when it comes to problems dealing with frames here. You could solve for the reactionary forces with the entire structure. Sometimes it may be simpler just to split up the structure into its respective members and solve accordingly.